in ages. The example that I was gonna be going through in this video is one that I first wrote it must be a decade now. I never got the chance to use this in teaching because I had a lot more examples. Then I forgot it, and about 5 years ago I then looked at it again because it seems interesting. So this Mandelbrot rendering, let's put the result on the screen for a while I'm yammering. So this Mandelbrot fractal used to be famous back in the day, but seems to have vanished. But its rendering makes for an interesting exercise, especially now we're gonna be harnessing the concurrency and parallelism to speed up this computation. Now, so 5 years ago, I looked up this example from Naftalin and noticed that in that time, I think even when run on the same desktop, then it seemed to run a lot faster because the Java virtual machine had, and its garbage collection and everything had become that much faster meanwhile. And now yesterday I was looking at this example. I'm gonna make a video of this, but since I've been recently reading all kinds of refactoring and design object-oriented design patterns and such material, so the source code it just started looking pretty horrible. So illustrating the principle that I once read in Hacker News or Stack Overflow, that in this field that if you're not deeply ashamed by the code that you wrote 5 years ago, so then you're just not advancing fast enough to keep up in this Red Queen's race. So then this morning I redesigned and refactored this as an exercise. So let's go through this version that I have now. So this kind of a Mandelbrot renderer. And first of all, so what is this Mandelbrot fractal? What is going on in here? So Mandelbrot fractal is this famous fractal defined on the complex plane. Now, if you don't know what complex numbers are, you don't need to worry about it. Just think of that the complex numbers are like a two-dimensional numbers, and then our ordinary numbers, they're just a trivial special case, one-dimensional line that's gonna be in this image. Actually, this center horizontal line in here, there are real numbers are just a special case of these two-dimensional complex numbers. And then the arithmetic operations like addition and multiplication, they're defined for these two-dimensional numbers, so that the one-dimensional number addition and multiplication, they're just special cases of this two-dimensional operation. But of course in 2 dimensions 2 is significantly different than 1, so then in 2 dimensions there is much more room for interesting things to happen. So this Mandelbrot fractal defined on a complex plane. So this fractal consists of this well-recognized black shape and then psychedelic colors around it. So what is a Mandelbrot fractal? What does it do? So every pixel now here corresponds to a complex plane. So we just use the complex point that is at the top left corner of the pixel. Pixels are small, but they do have a finite non-zero size. And then the famous equation that so you start from a complex number, so call it z, and then you calculate from that the next z by squaring your previous z and then adding your starting number where your entire sequence started from. So even when two sequences, if they have coincidentally happen to enter in the same point, so then because the starting numbers in both sequences were different, so then those two sequences gonna diverge. So here I was took a little zoom in there, so let's zoom into these smaller details to reveal this kind of infinity of complexity and smaller versions of this Mandelbrot set that are hiding. These look like they're disconnected, but as it turns out the black Mandelbrot set is fully connected. So all these black pieces are connected together by thin strands that we're not in enough resolution to see here. So if we zoomed in there, so we would then be seeing the thin strands emanating from the butt of this particular ant. So what is this this Mandelbrot fractal? Let's go back to the top level. So render the full image again. So it's an iteration fractal where so you start from a point and then start generating the series, and as it turns out, so there is two things that this series can do. So it can either escape from a given distance to the origin and then be guaranteed to keep escaping forever, and those then all those complex points for which the series generated from those points escapes this way, so then they are outside the Mandelbrot set, and as is customary, so the Mandelbrot set is totally binary yes or no, so then we should be rendering this background in one color, but I'd like to make this interesting psychedelic colors and shapes appear, that how many steps the sequence takes to escape across a certain threshold is then used to determine the coloring. And zooming through to this event horizon, so to speak, the edge of this black area. So this black area in the fractal then corresponds to the points that if you start generating the sequence from those complex number points, it never gets out. Like this black area is like a black hole that once you cross the event horizon, metaphorically, so then you'll never get out. You're just doomed to be inside there for infinity. But if you start from outside the black area, so then you'll eventually escape. So it can take arbitrarily long because so this fractal border, this event horizon, so we can find their points that take an arbitrary number of steps to escape. Like you could pick a number, or your adversary could pick a number, so 1 octillion. So we could in principle find a point that it takes exactly 1 octillion steps to escape. So then this event horizon borderline that surrounds this black area inside which you never get out, so then that is infinitely complex, and as you can see contains smaller fractal copies of the original shape gone through various small strange looking transformation, and it's all connected, and this has an effect of blowing some people's minds. So if we look at like a normal Mandelbrot renderers, if you Google for any renderer, so what they're typically gonna do is that they just determining this window. So what is the peephole that it gives to the infinite 2D complex plane? What's the coordinates? So then just for loop through all these pixels, and for each pixel, so do the iteration. So if the iteration escapes, so then you know that it's an escaping pixel, and then you paint the pixel accordingly. But the problem with that approach is that so when your for loop is generating the sequence from the pixels that are black in this image, so then of course that sequence is never gonna escape. So then you set up some kind of a threshold that once the iteration of a sequence has gone long enough, so then you accept that it if it's not really terminating, so it's at least close enough to the borderline, so that rendering that pixel black is not gonna be too big a mistake. But we realize that this is of course horrendously inefficient, so we're just wasting time achieving nothing. So these pixels, they're already black if we started rendering from a black image, so we're just doing massive calculations to keep them black. So that just really makes no sense if you think about it. So we want to spend these processing cycles to iterate these sequences only from the pixels that are actually escaping, so that we know what to color them. And now instead of for looping through all pixels, so now we can apply the techniques of graph searching, fancy term, but what's going on. But this is all like in the old joke that how do you carve a statue of an elephant when you just have a block of marble and a chisel and the tool. So it's very easy. So you just look at the block, and then you chop off every piece that does not look like an elephant. So then you get an elephant in the end. So kind of silly joke, but this approach actually works here. So that instead of for looping in two nested for loops through this 2D image of pixels, that we create the tasks. So every task is gonna be iterating an individual pixel. And if I show you in the source code, so that we get some variation to this video, just not hearing my voice. So we have in this Mandelbrot demo that starts with a whole bunch of these settings and variables. So we first, if we read through this casually, so just to get the idea. So first we have a utility method that from the escape count, so how many steps it took to escape, so then calculate the color. So we maintain a cache, so that an array, so that we distinguish cyclically between 1 levels. So then from the escape counter, so scale a little with the power that is less than 1, and then so when generating random colors, so here's a good sidebar also to make that don't just generate the random RGB values separately, because then you just end up with the very bland, boring looking colors. So use the HSP color space instead. So you have a hue and a saturation and a brightness. So make sure that you have a saturated and bright colors. So then you don't end up with the boring thing. Then you can adjust the scale of the hue what we're using. So here we're just calculating the hue just based on the a bit of a trick here with the different phases to create this kind of a color component interference. But so this class pixel, the nested class, so representing the task of generating the sequence of complex points starting from a given complex point. So reading through what every pixel knows. So every pixel knows its own image coordinates. So when the pixel escapes, so then it knows where to put the color in the image. And then so how many steps we've taken so far, and then for the purposes of organizing the search to age, so all these pixel objects that we create, so then we give them a running timestamp. So we have a timestamp generator, so it's atomic integer, so that it doesn't mind against the concurrency. So whenever a pixel object is created, so we ask the timestamp generator, give me a timestamp, so these each get a different identifier. And then so every pixel corresponds to a complex number on the plane. So we have I brought the utility class big complex that's there on the side, so complex numbers with like a big decimal from the standard library, so whatever precision we want to use. And so that's the starting point, and then this is the current point. So then there is also a Poisson pixel that is not really a pixel, but we use the object to pass around the messages in concurrency. So like whenever you get the Poisson pixel to process, so then you know that then you're supposed to be terminating, so you're all done. But so then every pixel as a method, you can ask it so continue your iteration for a given number of rounds, hopefully escaping. So we are asserting that this is not the Poisson pixel, so Poisson pixel we identify from the fact that its x-coordinate is -1, and then so calculating so for a given number of rounds how many to iterate, so that the new complex number point, complex plane point ZP is the current squared, so multiplied by itself and add then the next number. So then we can also so we can try other formulas like the cubic variation to create variations of the Mandelbrot set, and then testing. So if this complex number escaped to either direction, so then we mark them to make them to be null, so that they allow some garbage collection again, so that even if this pixel object continues to exist, so the garbage collection can still get rid of those two complex numbers, that they don't remain there as a memory leaks. And then we return the answer, so how many iteration steps were needed. And otherwise, so if the iteration still didn't stop, so then we're gonna be returning a negative number to indicate that this pixel still isn't done, that the iteration of that number still needs to be done. So then so to render this image, so if we zoom a little bit, let's zoom a bit deeper, so that we get a heavier computation. What is hiding in the, so yes, my color scheme is finally revealing some new colors. So as is well known, I don't have any artistic eye, but at least we get some variation there. But so this is now showing how the rendering is going, so that we have a queue of these pixels that are still being processed, and the queue initially just contains a bunch of pixels here on the edge. So for example, there was a pixel here where this line is going, and whenever iteration of some pixel terminates, so that it's a success, so it's colored, so then we add all its neighbors in the up, down, left, right direction here. So then we add those to the queue if they're not already been created and added to the queue. So then this frontier of the pixels that we are calculating keeps growing, and we have a bunch of concurrent execution threads executing in parallel. So each one always takes the next pixel from the queue, iterates it, and if it succeeds, do the rendering so render the pixel color to the image, and then just go on to do the next pixel. So all this work renderer execution threads, they're just repeatedly taking pixels to process it. There's a huge pile of pixels waiting to be processed, and then these threads determine. And then so when we initiate a new render, so for example doing this square zoom here, so then for the previous render to terminate it, so then we add a poison pixel to the queue. So whenever execution thread takes out the poison pixel from the queue, so then it knows that the rendering is complete, so then it puts the poison pixel back to the queue so that the next thread is able to receive it, and then all the threads rendering that the previous image know to terminate. So we're creating a whole bunch of new rendering tasks from scratch every time then the user zooms in. And so reading through this code a bit more, so next we can look at this pixel comparators, because this is also illustrating. So after this redesign, after all that reading on the design patterns that I did, so now this pixel comparator, so I was repeating myself in all the subclasses, and whenever you repeat yourself in your code, so like you know for a fact that your code is wrong. But so let's actually, while I talk about that, so let's just for a humor value look at this cubic version. So what happens if instead of x squared plus c we do x cubed per c? So let's start the rendering and see what happens. So we get a bit of offside here, but so if we zoom in, so what kind of shapes are we gonna be seeing? So now this Mandelbrot shape has it's like a deformed, so then the power like a kind of determines like how many arms and legs it has. So this Mandelbrot, so you could plug in like an infinite number of different functions there and see what you get out of a result. But as long as it's polynomial, I think then it's guaranteed that the black area is all in one shape. Okay, back to the code. So what was I talking about? So I was talking about the template method pattern here. So we need for the priority queue of these pixels. So there's all these pixels waiting to be processed. So which one should we be processing next? So let's look at the effect of using some of these different comparators. So priority queue data structure, just like the other order-based data structures. So you can give them a comparator strategy object. So something that tells which pixel is earlier in the queue. So which one is ahead of the line. So then implement the method comparator method compare. So comparing two pixels. So we do the comparison. So here's a template method illustrated. Gonna be soon after this. So template method is this protected method here that is used as a part of the execution of the whole thing. So template method allows us to say that the comparison of two pixels in all the subclasses also is gonna be taking this way. And now actually to emphasize this, so I'm gonna actually make this now final. So then this comparison is always gonna be done this way. So then the subclasses cannot change that, but they can override another method, compare pixels, that is used as a calculation step during the comparison. So in this comparison, so we see that so we decide that if either one of these is the poison pixel, so then that one's always the next in line in this queue. So that message is always gonna come first. And then so comparing two pixels, so looking at their iteration count, so which one was iterated less, so then that's the one that's gonna be next in line. Otherwise we delegate the method, delegate the job to this template method, that this subclass is DFS comparator, BFS comparator, center distance comparator. They just override this compare pixels method that we are calling. So DFS, so in the reverse order of ages and the breadth first search in the normal order of ages, and then the one that is used in the demo that we were just running. So we aim to get to the middle of the image. So let's say I'll show you what happens if we don't get to the middle of the image. So the pixel here, so a pixel comparator. So that's just the BFS comparator to demonstrate what happens. So now the breadth first search in the well-known fashion, as you can see, it's advancing. Well, it's a kind of effect, funny effect on its own also. But yeah, well, it's coming coming from the edges, which may or may not be wanted. But often the interesting stuff is happening at the center. So once this gets slower, so let's zoom in to make this slower. So we don't get, as you can see, we don't get to the interesting parts as quickly, but at least it's a fun effect. Now, if we're demonstrating the depth first search variation, we get an even more fun effect, more or less, but the depth first search. So now doing the searching in a depth first tentacle. So starting from the edges, so as soon as the pixels, the iteration terminates and neighbors get added, so the depth first search keeps zooming in like a tentacle. Well, here it looks like we have a sideways bias because these are mostly seem to be terminating, but let's zoom close to this fractal edge, and maybe we get a lot more action here happening. So yeah, so here we have a so now because yeah, I forgot what I also did here. So let's go back to this original. That if two pixels are like equally deep, so then we have a bias that we like the big X coordinate, and so no, we dislike a big X, and so then this tries to as a now bias to the top edge. We could, I guess, something like with the center distance comparator that resolve the ties in a different way, but at least we're getting an interesting effect now. We can see, so now the rendering of the individual pixel is slow enough that we can see the tentacle proceeding through. Now notice it's carving through the space like a turkey, and all the useful processing power is spent iterating pixels that still have a chance to terminate. So then eventually this is gonna start grinding the pixels that are at the edge of the black shape. So then those of course they're not gonna terminate. So these threads are not gonna keep grinding to these edges, chiseling away in a futile fashion when there's nothing more to chisel until they're mercifully terminated. So then those get terminated, and now we started the new one. So that's all these subclasses illustrating the template method. And then here I'm also illustrating now the singleton. So we have a singleton Poisson pixel that is shared by everybody. So I guess we could also make this one to be private final. So we know that it's never gonna be reassigned. Getting a bit of like some kind of a Tahiti colors here. So at least we get like interesting neon colors in this. So if so a bit of like a Miami Vice feeling here. So okay, so compute image. So this after the comparators and the pixels. So what is the compute image do? So we start by calculating the what is the size? So size of the is how much on the complex plane does the side of the image correspond to, like what is the size of the peephole that we're rendering, and then the big complex, so the complex number that is at the top left corner of this image. And then so to make sure that we're not adding the same pixel multiple times, so in each render we maintain a Boolean array, just to Boolean array the same size as how many pixels there are. I'm gonna stop this because it seems to be getting a bit slow, and I don't want this to terminate or something, run out of some resource. And then we create the buffered image in which we're gonna be rendering. And so then now that we're starting a new task, so we take a previous pixel frontier, and if there was one, so then we put the Poisson pill in there, and that is gonna guarantee that every worker thread that is rendering the previous image is next gonna receive the Poisson pill, knows to terminate in a good order. So maybe Poisson is a bit of a colorful name, so some kind of a termination node is might be more, but we get to have at least a bit fun. But the good naming is important. So that's also a code smell here. So I should clean up all the code smells from my code. So when I read the books and they ignored me. So okay, anyway, so then the priority blocking queue. So how many pixels are currently accepted? So I guess we could also make this one bigger and see what happens, which comparator, and then initialize, so the initial active pixels, so not every pixel on the edge, but every 20th or so, so that's already enough starting point. So because we know for a Mandelbrot set that so this whole black thing is one piece, there is no holes inside it, so the rendering from the edge is provided that you're not lucky enough that all your starting pixels fall into black tentacles, but maybe I think I'm gonna take that edge in here. So then a bunch of starting pixels, and then the rendering task. So it is a callable task, not a runnable, because I wanna be this day. So I'm not creating threads on my own here at all. Of course not. I'm using executor service in which these are submitted. So every renderer task knows so which priority blocking queue it's taking the pixels out of to process, and what is the display that it's rendering into, and numbers that we could tell them apart in debugging outputs. Probably not used in here, so I could also take those out. And then for the answer, we don't care about the answer, but so how many pixels were liberated from the black background color, how many were colored, how many were escaping from the Mandelbrot island. It's like a devil's island, but so once you're in the black area, you'll never get out. It might be like the California prison system. I'm watching too many videos. Okay, so then, so each renderer, so it also has its own ID for debugging purposes. We have another timestamp machine, so atomic integers. Think of it like a timestamp machine in a bakery that you take a timestamp, guarantees that everybody gets exactly one number and no numbers are skipped. And then the callable task that is being executed. So as long as there are pixels left to process, just as a failsafe, it's possible that we're rendering some area that has no black pixels, so then the frontier could become empty also. So then ask the frontier, so what is the priority next pixel to process? If it was the poison, so put the poison back and terminate ourselves, and otherwise iterate that pixel, give a number of rounds, that is also, and if that was a success, so then that was success, and now just to be safe that because updating, of course, the buffered image for efficiency reasons is not thread safe at all. So we have one global mutex shared by everybody, so a pixel mutex, so a critical section that we can update this pixel, and then more importantly also update this Boolean array. So it could theoretically happen that the two threads simultaneously try to create the same pixel coming from different directions to it. So make sure that only one of them. So then now that this pixel mutex guarantees that the critical section, only one thread at a time can be executing it, so then we can read and non-atomically we can access and modify this local frontier, because it's a thread safe priority blocking queue, so it doesn't need our synchronization, but of course doesn't hurt. So we create these new pixel objects on the fly as soon as the search reaches those pixels, searching from the edges, and the pixels that correspond to the inside the black hole area. So we never spend 1 byte of memory or 1 processor cycle in even evaluating those. So it's just a massive saving. So this method, for as many renderers, so that's another of these named constants there. So just create a new renderer task and submit to the executor service. The executor service maintains a queue of tasks and an internal thread pool that it allocates to the task. So whenever one active task terminates, so then the next task from the queue is gonna get executed. So because we submitted the poison pill before adding this renderer, so this is gonna guarantee that all the previous rendering threads are gonna be terminating, so that the threads that we submit here, they're gonna have a good time executing. And then just the actual construction. So we just for the purposes of this zooming effect, this kind of very simple drag box. So we just listen to the mouse motion. So there's notice that the Java swing And AWT, like as a mouse motion and mouse listener are two separate things, so it's a bit of oscillating. Then this mouse wheel is a third thing altogether. And then, so a mouse listener, so I want to react to the mouse pressed and mouse released, not to the mouse clicked and those, because I don't need to distinguish between the gigs. So the mouse pressed, so starts a new, so BXBY are the stop of the drag box. And so start and the something, the coordinates of the drag box, and then so a mouse release them. So if you release small enough, so then it's like you're not zooming, so you don't have to commit to your choice. And then otherwise, so just calculate the complex plane coordinates that are in the drag box, and then initialize a new rendering. And this method, as we just saw, so is gonna issue the Poisson bills to the previous Frontiers renderers, so that it's the new renderers they get to start right away. Paint component is very simple because we're rendering everything into an image, so the paint component is just essentially one line. So this one I have here by habit. I think we could even comment it out, because so this will empty the whole component. Nothing guarantees that the component stays the same size, so I guess it's a good start. And then the zooming, the drag rectangle only if one is defined. And it's very important that so whenever you create any swing component that has a background computation inside the executor service changes nothing here. So we have both the animation timer and the executor service. So executor service has the nice thing that we can just tell it that all right, you're done. So no, just to interrupt and terminate all the threads. We don't even need to hear wait. We could also issue orderly shutdown. So let the things, but then we would have to issue the Poisson bill also. So let's just make sure that everything terminates. So this Mandelbrot, so this is a pretty fun example that we can now use to illustrate a whole bunch of things. So let's bring back the original, the standard brot. We're still doing the depth first search. So let's zoom next to the edge. Looks like my computer's running very low on resource. It's getting slower, so I'm gonna terminate this video now. So this is getting half an hour already. So hope you had a good time watching this video.